So let's move on to the next speaker, António de Morais, also from the University of Aveiro, and he is going to talk about gravitational waves from supercooled phase transitions in conformal neutrino mass modes.
Okay, thank you very much. But before everything, what is the pointer? Just there is no pointer. Okay. I thought it was. If it works, it can be helpful. I thought it was. Diz.
Queres usar para mudar os textos?
Tem que pôr aqui, não é? Se puder ser.
Não tem isto lá, não. É só automático. Podes usar aqui e tens aqui o.
Ok. Perfeito.
Não está a funcionar.
Eu mudo aqui também se for preciso. Ok. Okay, so once more, thank you very much, and for me it's an honor to be the closing talk of this wonderful event, and I want to thank very much for Luis that was very hospitable all this time, and of course for everybody else, and this has been a wonderful time here. Right, okay, so so I'm a particle physicist, but I work in this intersection between high energy physics, cosmology, and as you can guess by this title, I'm looking into gravitational wave observables, so there is here also a clear connection with gravity, although not in the same geometrical, neat way that you guys are working. So I will try to, this is going to be a little bit different, but hopefully not that strange, and I hope I can convey some interesting message that for us particle physicists, this gravitational channel is very important. So the work that I'm going to show was done with my PhD student, João Gonçalves, and my collaborators, Dani Marfati from Hawaii University and Roman Pasechnik from Lund University in Sweden. So this was supposed to have already appeared, but we wanted a bit more data, so in principle, only next week. But we are not going to fail this 24/11 here in principle. Okay, so, and here I need to use this. Oh, it's not going anywhere. I don't know what's happening. Okay. Now I can also use this picture. Okay, so first of all, so you know that the standard model is boringly successful. So it's basically is successful in explaining most of its predictions, but it's clearly incomplete. And to start with, neutrinos in the standard model are massless. So you don't have a way to give masses to neutrinos within the framework of the standard model. Also, the standard model does not contain dark matter. And these two, I'm underlining these two because are the ones that I consider the most overwhelming, overwhelming phenomenological evidence. I'm keep being bugged by several things here. And the ones that I'm interested to work about recently. But there is also like why our world, why we have this material world, why we don't live in a world of radiation. Well, we would not live there, but why there was like an imbalance of matter and antimatter in the primordial universe that today our world is made out of matter. Also, on a conceptual side more, we know how the masses in the standard model, the masses of our particles are generated, but we don't know why they are what they are. So we know the Higgs mechanism is what gives the masses, but we don't know why they have these large hierarchies. Why is the top quark so heavy? Why are the neutrinos 11 of an order of magnitude lighter? Why the quarks mix in a hierarchical way? I mean, you have hierarchies, so large mixings versus tiny mixings. And why in the lepton sector you have like a more democratic mixing? You have like sort of order, not unity, but angles, mixing angles that are of more or less of the same order. the so-called PMNS mixing versus the CKM mixing, the one in the quark sector. Also, conceptually, we don't understand why the Higgs mass has chosen the electroweak scale rather than the Planck scale or any other scale. So these are things that we are trying to understand. All of these are intensive research directions. I will not solve all of them. I will address mostly the first and a little bit of the second at the end. But what I can tell you, and this is the wrong direction, is that to solve these questions, typically we can extend our scalar sector. So beyond the Higgs, you put more scalars, and also new gauge symmetries to try to have an organizing principle behind phenomena. And the key point here, the catch here, is that when you do this, your vacuum structure, so beyond what you have in the Higgs sector, becomes more complex, so you have a richer structure, and this allows to something that cannot happen in the standard model, like a first-order phase transition. It's a finite temperature effect that you can have. And this is one of the consequences. It's not a motivation for, but it's one of the consequences of extending your scalar sector. So you extend the scalar sector to explain dark matter, for instance, or neutrino masses, and then you can get for free, in some cases, first-order phase transitions. And this is the point, the connection to gravity starts here. Because these events happen in the early universe, and so you can have, and I will explain that a little bit with some pictures, phases of a new vacuum, a bubble with a new vacuum expanding in a universe filled with a false vacuum, and those bubbles expanding, they will give rise to a stochastic gravitational wave background. I will explain a little bit more about this. So essentially, just to put this in context, this stochastic gravitational wave background, so here you have the bubbles. So this is something that happens, it's physics pre-Big Bang nucleosynthesis era. And it's a gravitational analog of the CMB, essentially. And today we know that we can have like this visible light, and possibly we'll be able also to have information from this era through gravitational waves. And we can really start disentangling what was going on in complementarity to what collider experiments also try to do. Right, so in fact there is overwhelming evidence for the existence of a stochastic gravitational wave background. So you know this pulsar timing array, so there is some excess which is pointing towards the existence, at least in the nanohertz region, of this stochastic gravitational wave background. And this is just an example, just some estimation that they have done, so this the nanograph collaboration, saying that, and here I'm focusing phase transitions because this is what I'm going to focus on. So that signal or the evidence of that signal can be, in principle, better explained with new physics. So it's of cosmological origin, or cosmological origin plus supermassive black hole binaries. But it's the likelihood seems to be, in some scenarios, to be favorable to against only supermassive black hole binaries. So this is, in a way, quite tantalizing. And it's only motivational. This only serves a motivation. I'm not even going to these frequencies, to these nanohertz. I'm going to be a little bit at higher frequencies. But anyway, this is tantalizing, and I think we have good times ahead and promising times ahead. Right, so but what is this about the first order phase transition? So let's place ourselves in the early universe where the temperature was really high, and we are living in this vacuum here. So where a massless vacuum, so there were no masses here. Then the universe started cooling down, and at some point you have another vacuum that is developed and gets energetically equivalent. So this is what you call, how you define your critical temperature. So there is still no transition. We are still living there because it's not favorable to transit to the other vacuum. But as the universe continues to cool down, this vacuum will become deeper. And at some point, there is a certain probability to nucleate these bubbles grows, and they start nucleating in different patches of the universe. So part of the universe in gray is still living in this vacuum, and in the orange one, they are already living in this vacuum, and these bubbles are expanding. The universe keeps on cooling down, and then you reach a temperature where you can have a causal structure connecting. Yes, Uli?
Sorry to interrupt you.
No, absolutely.
But I'd like to follow. The curves you're plotting at the
It's on, it's on.
good. The curves, they are potential, I assume, right?
This is a potential.
These are
yes.
potential
Yes,
functions,
yes.
like for an inflaton or something.
For example.
Now, are there evident mechanisms why this potential would be temperature dependent?
That's a correction that you put in your potential. The potential is not necessarily temperature dependent, but then it's corrected with temperature. It's a quantum correction, basically. It's a correction in the realm of thermal quantum field theory.
I see, because naively, I regard high temperature as a kind of someone shaking particles in this potential well.
Mm-hmm.
And then actually, as you decrease the temperature, you shake less. So intuitively, that would indicate that it's actually less likely for the particles to move to another vacuum. But you are actually, what you are saying is that these are quantum corrections that actually change the potential.
They do change it. So this evolution is temperature. This vacuum becoming deeper is a temperature correction. Or I mean, in other words, it's like in this direction. So we live here at 0 temperature. We live here, but you heat up and you restore the symmetry. And this is actually quite easy to see. So if you have a potential, for example, mu squared plus lambda, so mu squared phi squared plus lambda phi to the 4th. So it's simply this, it's a quartic potential with the all positive parameters. Now, if you put a minus sign in this mu squared, so you have a minimum, right? So this is, now, the corrections, the leading order corrections are of the order C, with some constant, which depends on your particle content, times T squared. So it's an effective mu. And it's positive.
Okay, that explains why I've always struggled to understand how exactly this happens at lower temperature.
Exactly. But you see, you generate an effective positive mu squared at higher temperatures, and then you restore the symmetry. Of course, you can have exotic situations where this C constant is negative, and then the restoration is at low temperature. So this is not like only one possibility. And that gives rise to really nice and exotic possibilities, like not symmetry breaking, but symmetry restoration in the late universe.
Thank you very much.
My pleasure. Okay, so thank you, Uli. So this was actually quite helpful to even say a few more things that in this regard. But the point here is that this percolation temperature, this TP means percolation, is defined when your universe, basically, all the bubbles are causally connected. This is the simplest way to put it. And so you cannot go back to the previous phase. And here at this stage is where we define. This is, of course, a choice what we think it's more convenient, but there is still some debate if we should let it cool down more or not, or exactly what is the condition to set this. Anyway, there are a few technicalities. This is just the message I want to convey. But here you then pick up your particle physics model, because this potential is where the information of your particle physics theory is. And you calculate these thermodynamic parameters. So alpha is basically is proportional, I will show you, but it's proportional to the variation in potential energy, basically from the false to the true vacuum. This beta over h is the duration, so the inverse duration. So the smaller the beta, the longer lasting is the phase transition. So it's a very important parameter, and these two parameters will show up several times. And the percolation temperature. And also there is another one, which is this reheating temperature, which is important. It always happens, but this is only important when this alpha is huge. It's really several orders of magnitude above unity. Because you enter in a period of thermal inflation. This behaves as as a cosmological constant. It's not a cosmological constant, but it behaves as if it was a cosmological constant. So you have accelerated expansion during a certain period of time. And therefore, when you enter radiation domination, you need to redshift your stuff, you basically, according to this reheating temperature, which is all the energy that was stored in this false vacuum that then is dumped through latent heat into the universe, to reheat the universe. When this alpha is small, order 1 or below, then these two temperatures are almost identical. Okay, so these thermodynamic parameters, so I will repeat the thermodynamic parameters, they capture the information of your particle physics model, and then they will be translated in this stochastic gravitational wave background, so SGWB is the stochastic gravitational wave background. This represents the sensitivity curve of an interferometer. Doesn't matter which one now, but let's just consider it can be LIGO, Einstein telescope, LISA, and this is the spectrum. Now, you have your reheating temperature, and the reheating temperature, or percolation if alpha is 1 or smaller, will basically define the frequency, so the peak frequency. Now you have this alpha. So I told you, so this is the variation in potential energy over the radiation energy density. And this will basically shift the spectrum up and down. So you can see when you have a lot of latent heat released, basically when this delta V is much larger than the radiation energy density, so this spectrum will go up. And then there is this beta, so the beta over h, so this is the duration of the phase transition, which shifts in both directions, so diagonally like that. But when you are in the limit of strong supercooling, basically when this alpha is much larger than 1, basically this becomes approximately constant, and also the spectrum of gravitational waves, which, so here you have alpha over 1 plus alpha, so if alpha is much larger than 1, this becomes a constant. So you cannot go indefinitely up to infinity. Even if you put alpha up to infinity, there is a saturation point. Right. And what are the sources of these gravitational waves, these primordial gravitational waves? So here it's represented like the false vacuum in red, the true vacuum in blue, and you can have bubble collisions. So here you see the bubble, so the bubble walls collide, but these are only efficient when these bubbles undergo like this unbounded expansion. So when they expand at the speed of light, essentially. Because there is friction in this plasma, and this will stop or prevent the bubbles from efficiently colliding in most of the cases. And then, in those cases, which are the most of them, sound waves are the dominant contribution. So these are represented by these wave fronts that here in front of the wave. They can be supersonic, they can be subsonic, but they all give rise they can all be efficiently converted into gravitational radiation. And there is a third, which is very difficult, very expensive to model, so this magnetohydrodynamics turbulence. So you know that magnetohydrodynamics simulations are really complicated and actually not very well understood. I was in the LISA cosmology working meeting, which was in Porto actually this summer, and there were like 5 presentations about magnetohydrodynamics turbulence and 5 completely distinct results. So the only thing that plays in our favor is that they typically contribute to these tails. That's more or less what is unanimous. They change a little bit these shapes, at least for now. That's why I'm saying it. At least for now, this is the understanding. So I will mostly focus on bubble collisions and sound waves because I'm only interested in the peak. So in this position of the peak. It's where the particle physics information is stored. So everything else is hydrodynamics, essentially. And also, just to say intuitively, so this turbulence, the magnetohydrodynamic turbulence, is when you have like all these wave fronts, they interfere. So these sound shells, they interfere, and it's one of the sources of turbulence. But there are a few more. Okay, so now after this introduction, let me come down to a class of classical scale invariant. I will explain what is that. U1 prime models that explain neutrino, all neutrino oscillation data. So basically, all neutrino physics is explained in this class of models. And U1 prime, it means any sort of U1 that can generate neutrino masses. So that's the constraint. Of course, I will focus in one specific scenario for concreteness, but that is you can extrapolate for more generic U1s. Okay, so just to set the stage here. So here you have the standard model, the quarks in the standard model, the leptons in the standard model, so the left doublet, the electron, right-handed electron, and you have 3 generations of each of this stuff. The Higgs doublet, this is a right-handed neutrino, and this is a scalar, like the new scalar in this theory. What your extended scalar sector is basically this complex scalar. So it has a U1 charge, so this is a complex scalar. Now, these charges here, they are not ad hoc. To get to these charges, and you see they are dependent on this XH and X sigma, so they are dependent on the charge of the Higgs doublet and the charge of this complex singlet. And this form of the charges needs to comply with the anomaly cancellation. So this is well, it's a quantum field theoretical concept, but you need these anomalies to not exist, otherwise you would break gauge symmetries at quantum level, and you don't want that to happen. So you have a gauge symmetry, and this gauge symmetry needs to be protected radiatively. So if you do radiative corrections, quantum corrections, the gauge symmetry is there and acts normally. So if you have anomalies, then that's a problem. It's a pathological theory. So this is calculated in order such that your theory is healthy in this regard. Now, you have also this classical scale symmetry, or it can also be, it's a special case of a conformal symmetry. I think the simplest case. So classical conformal symmetry, you can also call like that. So essentially, so you have this simple transformation in the coordinates. So this rho is a scale factor. That's the name of classical scale symmetry. And you can also transform your fields according to this rho to this power of A, where A is -1 for bosons and -3 for fermions. And if you look to your action, I can try to convince you with the phi to the 4 theory. So in the phi to the 4 theory, you have here, so this, since it's -1, you have your Lagrangian goes from phi to the 4 to rho to the power of -4 phi to the 4. But in your action, you have a dx4. And the x, you have a rho. So 4 rows here that will cancel with the 4 rows in the Lagrangian part. So, and it happens the same in the fermion sector. In fact, the standard model is accidentally classical scale symmetric, apart from the Higgs sector. But the gauge sector and the fermion sector has this accidental symmetry. For the neutrino sector here, now, so on top of the fermions of the standard model, you have these 2 extra terms here. So this is what is called this Y nu. This is a nu letter here. I don't remember the name of the other letter, but this is a nu for sure. And this Y nu Yukawa interaction, so couples these right-handed neutrinos with the Higgs doublet and with these lepton doublets. And then you have another term, it's the so-called Majorana term. So this is the Dirac neutrino term. You have also a Majorana term where it has 2 of these right-handed neutrinos and this sigma. So essentially, what you do is you break the symmetry, this U1 symmetry with this sigma, and you dynamically generate a mass to these right-handed neutrinos. And then later on, at a later stage, when the electroweak symmetry in the standard model is broken via the Higgs mechanism, you also induce a term, so you're going to have a VEV from this H here, and you generate a mass to your light neutrinos, also to the heavy, so 3 heavy neutrinos, which are going to have this scale, this V sigma, and you have a mass for the neutrinos, and you see that they need to be tiny. They need to be tiny, but you see, so they go with the ratio of the electroweak scale, so 100 GeV squared here over this V sigma. So if this is large, like the gut scale, 10 to the 16 GeV or so, even if all of these are order 1, so you get into this ballpark. So this is the type 1 seesaw mechanism, but a conformal one, let's say. So instead of putting here a mass term by hand, so the type 1 seesaw mechanism on its own, it's this plus a mass term here. You don't have the sigma. You put an m here and n. So m of mass, neutrino mass, heavy neutrino mass. So, but it's a parameter that is not being dynamically generated. You are not explaining where is that parameter coming from. Here we are also trying to explain where that parameter is coming from, basically from the breaking of this U1 symmetry. Your scalar sector is this, so you have, because of classical scale invariance, you don't have mu terms, so this dimension full parameters in your theory, but you have this quartic coupling. So this is the Higgs part, this is the singlet part, and this is the portal. It's called Higgs portal. This is the communication to the standard model is made through this interaction, which in our case here it's going to be tiny. Right, so when you have this classical scale invariance, this is not a true symmetry, in fact, like a gauge symmetry is. Because I was telling you before that the gauge symmetry needs to be protected against quantum corrections, but this one is not classical scale symmetry. That's why the name classical is here. In fact, so when you go to one loop, so radiative corrections, it's quantum corrections, this symmetry is not protected and it's broken explicitly. But back in the day, back in 1976, Gildner and Weinberg, so the Steven Weinberg, so they have shown that if you consider, okay, there is a vacuum out there which is radiatively generated, but if you look into the generators, the group generators and so on, you realize that if you rely only on the three-level part, assuming that there is a vacuum that is out there, you get, in this type of model, one massive and one massless state. This massless is a pseudo-Goldstone of this classical scale symmetry, which actually is not massless because this is only the three-level approximation. In fact, that is massive because then you have the quantum corrections, this VCW. And CW stands from Coleman-Weinberg, but not the same Weinberg. It's another Weinberg, it's Eric Weinberg. And these guys have shown that from a purely quartic theory, with a purely quartic potential of the sort of the one that I've just shown, then you had quantum corrections, and which are of this sort. This is well defined. Here I'm only putting the result. And if you see here, so you have a log term here, and the log starts with negative values. So you see you are summing a positive and this negative, so you generate this minimum, essentially. And as you go to infinity, you have phi to the 4 times log of phi, which will grow faster than phi to the 4 alone. So that's why this is unbounded as well. This potential is unbounded. So it's quite a healthy potential. And when you have this, then you have all your masses in your theory, which are dynamically generated. And there are a few advantages of this. First, this dynamical symmetry breaking is on its own a nice concept, but maybe this is only my personal opinion. Then you have a lot less freedom, so your theory is more predictive. So in particular, you only have one free parameter in the scalar sector, which we can choose to be any, but here we are trading for the mass of this guy here, the new Higgs boson. So H1 is going to be the standard model Higgs boson. H2 is going to be the new Higgs boson, which can be much heavier than the standard model one. And when you set this scale, basically you are setting the scale of your theory through these quantum corrections. In the gauge sector, you only need have a free parameter, this gauge coupling. So this is the interaction strength of your U1 prime theory, and the charges. And in the neutrino sector, so you have, here I'm going back on 1 to C. So here, this will be input, because we need to make sure that the mixing is out there. But this Y sigma here is going to be, you're going to have 3. We are taking this as diagonal for simplicity here, because it doesn't make difference for the gravitational wave studies. Actually simplifies our life. You can still get the mixing, the masses, everything. So this was a simplicity approach. And you have 3 more, but you still have 3 parameters here. So basically, we are going to work with the trace of this guy throughout. because this guy will enter this Coleman-Weinberg as a trace. Right, and the one that is more important here is that there is rich stochastic gravitational wave predictions due to strongly supercooled first-order phase transitions. And now let me explain what is this supercooled first-order phase transitions. What I meant by supercooling here, in fact, because I've been saying this several times, but I have not yet explained. So let's put ourselves in the high temperature regime. And in the high temperature regime, already with the corrections from the zero temperature and the finite temperature part, you have like a 5 to the 4 component, which has the 3-level part, so the classical part, which is only this lambda. Forget about the Higgs sector now. The Higgs sector is decoupled, so this is also convenient. We can work only with the one field direction, which simplifies our life as well. So we have this 3-level part, and then all of those that have these pi's in the denominator come from quantum corrections. And in fact, here these are zero temperature corrections here. You see, so the trace of this, basically there's a power to the 4, so it's not immediately the trace here, but you have this y sigma entering here, and the GL gauge coupling, so everything is entering at quantum level in your potential. Now you have a cubic term and a quadratic term that are thermal temperature dependent. So at zero temperature you restore your classical scale invariance. It's only 5 to the 4. But here you have this cubic term, so 5 to the 3, with a minus sign, which means that you are going to have a potential barrier. And then, so these lines, this is a zoomed in version here of this one potential here. And the message here is that at zero temperature there is no barrier, but at higher temperatures, as you grow the temperatures, the barrier goes higher and higher, as suggested by this high temperature expansion of your potential. Right, so what's happening here is that the point is that as your universe cools down, you have a potential barrier for a long time. The potential barrier is there for a long time. It's not only a correction on a potential barrier that might have been there from the beginning. So if you had already a 5 to the cube term in your potential, you would have only a small correction, and the phase transition would be active for a shorter period. But here, this phase transition is active for a long time, which means that the true vacuum will cool down a lot until low temperatures, and this is why we have supercooling. So this is the feature, a unique feature of this classical scale invariant scenarios, which gives rise to large alpha and also small order 10 to 100 beta over h. So very long-lasting phase transitions and very strong phase transitions. Right, so this is just a few technicalities. I'm not going to waste much time on this. Just to say that we have little freedom, and because of we are considering mass scales that go from electroweak scale up to the Planck scale. We are going to explore all these scenarios, but then you know that when you have a quantum theory, the couplings, I think you have already heard about the running constants. This is a feature of quantum theories. So your couplings, your constants are not really constants. They run. So they are momentum dependent. So they depend on this t, which is the renormalization scale, over some reference scale, which we are taking to be the Z boson mass scale. And they should be rescaled when you go to larger, so higher, basically to higher scales, which is set by this the second Higgs boson mass. Okay, so now the first results here. First of all, you might recognize here a few interferometers. So this is the sensitivity curve of LISA. Here, this is the Einstein telescope. Here you have LVK. I think this was up to 04 data. And this here, it's LIGO 05. So it's the projected sensitivity of LIGO 05. So the first thing that I want to point out here is that there are several points within LVK here. And these were not observed, so this should be excluded. So we are already, I will elaborate a bit more on that, but here we are already excluding some scenarios that fall within LVK. Also, another thing that you see is that the interaction strength of your gauge theory will define the energy density amplitude. So this is this h squared omega. So it's related to the strain. There is a direct relation from this to the strain, which is what I think you are more used to. And so this is because when you have your potential, and as I told you, there is a running of the couplings. So your potential at leading order, so this is given by this lambda sigma, it's the quartic coupling of this sigma. This lambda sigma runs. It starts as negative, and that's why the potential is pointing down. Then you go up in scale. This eventually crosses 0. There is an inflection point, and then goes to positive values, and you generate the minimum, and then it's bounded from below your potential. And what you see is that the equation, which we call the beta function of the RG equation, the renormalization group equations that define the evolution of the parameter here, this coupling, it's basically dependent on the gauge coupling. This is the dominant contribution. So what's happening is that here, you see, if you have a larger gauge coupling, you have a faster running. So it will pass through 0 before, which means that your minimum will be shallower. Whereas in the scenario where you have a smaller gauge coupling, the minimum will be deeper, which means that the potential energy difference will be maximized when you have the smaller GL, which means that smaller GL, larger energy density, because the larger the difference in potential energy, the larger the energy density amplitude of the gravitational waves. So the key message here, if you observe something along these detectors, and if you interpret that in terms of this class of models, you can start saying something about the interaction strengths, and with quite some precision, actually. This is quite paradoxical, because somehow you have more precision in this than in colliders to this type of couplings. And the precision is not coming from the experimental size. It's coming from the vacuum structure. It's highly sensitive with respect to these couplings. But you see, you can start saying something about these couplings. This is just a thermodynamic parameter, just to say that the supercooling starts here in this region, more or less. Below, it's mild supercooling. And there is a translation in values of beta, which are smaller than 100, and this is the same GL. So here the colors are not very easy to spot, but it's values that are below basically 0.4, between 0.4 and 0.3 approximately. Right, now, what about the frequency? So we know what is setting the amplitude, and now the question is, what is setting the frequency? The frequency is set by the temperature, as I told you before, this rating temperature, but the temperature captures the scale of your theory. Essentially what you have here, so this is the gauge boson. I think for you, if I call it Proca, it's a real Proca field. I think maybe you are more familiar with that nomenclature. And this is the scalar. And you see, so their masses are not identical, but they are related. They are 1 order of magnitude apart because of the quantum nature of this H2 mass. So there is suppression, quantum suppression, but it's about 1 order of magnitude only. But the behavior is the same. And you see, the lighter they are, and it goes down to something like, 10 to the 10, like 10 TeV or 1 TeV for the H2, and it falls in the LISA region. And when you go up to the GUT scale, 10 to the 15, 10 to the 16, it goes in this region that can be tested with LIGO, Einstein telescope. So these different experiments can really test different regimes. And these regimes are not at the reach of colliders. So this is something, but imagine if you see something, for instance, at LISA, you can then maybe have this, what the particle physics community is needing in order to build a new collider. If you see some overwhelming evidence of this and a scale that everything is pointing towards a scale which is around 10 TeV or something like that, then that would be a strong motivation to build a collider like the FCC. So the gravity community can also have great contribution if you guys can do well in the experimental side of these interferometers. It's very important. And there is also connection with the neutrino sector. This is the seesaw mechanism at play here. So once again, all the scales are connected. It's the same shape. But the interesting thing here is the Yukawa couplings, the Dirac Yukawa couplings, the ones that couple with the Higgs. So they are order 1 at this high frequency, in this high frequency region, and they are order 10 to the minus 6 in the low frequency. But it's a pretty reasonable. So this is the so-called regime of the low-scale type 1 seesaw. This is the regime of the high-scale type 1 seesaw. And you can cover pretty much all of this with these experiments, as you see. Even this BBO, which is only on paper, we are using this because it suits our purposes. We have several points that fall here. These are only the peaks of the spectrum. But LISA, Einstein telescope, LIGO, these are experiments that will happen. And I think if astrophysically even we keep on seeing interesting stuff happening in LISA, Einstein telescope, BBO or some analogous experiment will also come online. This is at least my guess. Right, but there is here a catch. What if we decouple the heavy neutrino sector? So as I told you before, there is this period of thermal inflation where this second Higgs boson behaves as a thermal inflaton. And if it's decoupled, it does not communicate efficiently with the standard model. So it oscillates in this vacuum, behaves as an inflaton, and you enter an early matter domination period before it can decay through the portal with neutrinos, and even direct couplings to the standard model, and entering finally radiation domination. So this means that when this happens, when you are decoupled, you need to redshift your spectrum. And this is a quite overwhelming effect. So you see here, it can be 10 to the minus 15, which see the suppression that it does in the energy density amplitude and in the frequency. So this, the suppression is quite overwhelming. So you would not see anything in these Earth-based detectors, only within LISA. And why am I showing this? So first of all, if we see something here, this is a signature of the presence of again, interpreted in the scope of these models, can be a signature of the presence of neutrinos, of these heavy neutrinos. But if we look to the simplest scenario, let me skip this one. This is just okay. This is just a scale. This happens when this H2 is larger than 10 to the 5 here, and because this behaves, there is a relation of this decay ratio over the Hubble, which goes with this power of H2. But what I wanted to say is that if you compare this with the simplest scenario, so this is in this paper, where you have a U1 dark symmetry, they only wanted to explain dark matter here with a classical conformal, no neutrinos, and they realized, so the charges are different, so this U1D, everything is 0 because it's a dark symmetry. These right-handed neutrinos do not exist, and you only have a charge for this sigma. And in this scenario, what happens is that they could predict this spectrum at large frequencies, but then because of the matter, this matter domination period, there is this dumping, which has actually the same shape. So this blue corresponds to that. So these ones correspond to these ones like that. So at low frequencies, there is no difference. As you have seen here, there is no difference at low frequencies. But at high frequencies, then it dumps down like that. So there is a clear difference here between the very similar models that want to explain a completely different phenomena. Neutrinos on one hand, dark matter on the other hand. So this was the message about this that I wanted to tell. Now, of course, if we decouple, we can also wonder, what if they are very strongly coupled, the opposite? Then this Yukawa coupling starts competing with the gauge coupling in your potential. So, and the easiest way to see this is recalling that this lambda sigma, and I should go up just to refresh your memory, so it can be here. So you see the potential is dominated by this scale-dependent parameter, so this lambda. And this lambda, so recall this discussion here. So this lambda here, there will be another effect. So this was the effect that was out there before. And now we have an effect of this y sigma, the trace of y sigma to the power of 4. And, okay, this is written for a generic charge here. That's why there is this 6 and this x sigma. What happens is that this has the opposite sign, so they compete. Which means that when you grow this y sigma, you will further slow down the evolution of this lambda sigma, so you will allow to even deeper minima. That's why you can go to even higher frequencies. So recall that previously we had only barely got here to the limit of LIGO and a few things in Einstein telescope. But now we can strongly populate all this region going up to like 10 kilohertz region, more or less. And this is an effect of the right-handed neutrino sector in this model. So even the right-handed neutrino sector is playing a role here, which is very important. This is, of course, only evident at higher frequencies. You cannot really disentangle it at lower frequencies. And there is more dispersion because you have more parameters competing, of course. So it's not as neat as before, but the trend is still there. Right, so overall what we can do here is then we look to the experiments, we calculate the signal-to-noise ratio, assume like 4 years exposure. This is, well, standard. Of course, for LVK, it's not 4 years exposure, it's the data out there. So here, this is the LISA, the region where you're going to have a signal-to-noise ratio larger than 10. So you need a signal to, this is what at least the community is saying. So you need more than 10 in signal-to-noise ratio to be able to distinguish a stochastic signal like of this sort. And this one is the Einstein telescope, so there is strong overlap here with LISA, and so the higher frequencies of LISA correspond to the lower frequencies of LIGO. And here I'm considering not only the points, it's also the full spectrum. The tails, if they enter the detector with a signal-to-noise ratio larger than 10, it's accounted in here. This is LIGO 5, and this is LVK. So this is excluded here. Of course, here I'm taking the scenario where y sigma is not playing a role in the vacuum. But this region here is excluded. And the other ones will be tested. And interestingly, the supercooling, I've shown you a few slides back that supercooling happens basically when this GL is smaller than 0.42, something like that. So you can really cover all the supercooling region. Even if you don't see anything, you can even rule out this possibility with gravitational experiments. But of course, if you have this strongly coupled, strongly but perturbative, it's not strongly coupled as like the QCD. It's like a competitive value of y sigma with GL. You have more dispersion, but you can still probe a lot of regions. Even here, you can also, more or less with this y sigma trace, y sigma in 0.5, you can test with all these experiments. So this is quite promising in this regard to test this particle physics in a pure gravitational setting. Okay, this is now the last section that I will show you. And so yesterday, Caio and also Dario, before they are great gravitational physicists, and they want to explain dark matter with a scalar, with a particle, and I'm a particle physicist, and today I want to motivate dark matter with a black hole. So there is here some paradox, but it's what I'm going to tell about this work in progress. This is not yet a fully digested work, but I think there is already some nice features, and given this audience, I took the liberty. I will say as well, I hope my collaborators don't mind me already, so please no one scoop me, but of course I truly believe you. Okay, so let me go to this. So there are several mechanisms for primordial black hole formation. And let me say, this is related to the previous. It's not, don't disconnect from the previous discussion, because this is the follow-up. So there are several mechanisms, collapse of cosmic strings, dominoes, etc. But the ones that are relevant in this scope are so cosmological first-order phase transitions, in particular, the collapse of delayed false vacuum patches. So this is the picture, which I stolen from this article. So you have, when you have this strong supercooling, as I mentioned, so this alpha can act as a cosmological constant. And this is a stochastic process, so it does not happen in the whole universe at the same time in the same way. No, there are places where it will happen more or it will happen less. And it can happen that you have like this called late bloomer, so a region, a causally connected region in the universe where no phase transition has taken place. So this is a vacuum dominated, so this vacuum energy dominated and not radiation region, which will inflate faster than the surrounding medium. Then you will start inducing phase transitions there. They will eventually happen. But this has inflated more, so you have, let's say, more space. And when you percolate into the new phase, you will have an overdensity of the radiation energy density than what you would if it was not inflating. And this, under certain circumstances, this overdensity, if it passes a certain threshold, it can collapse in a primordial black hole. And this primordial black hole is a candidate for dark matter. So now relating this, picking up our previous data, not all, only some selected data with this really large, really small bit over H, so very long-lasting phase transitions. You see, so there is this line here which has the following meaning. So first, FPBH is the fraction of dark matter in the form of primordial black holes. Now, you have this shaded area which is excluded, and above this line of FPBH equal to 1, you have its overdensity of dark matter. Basically, it's not viable. Below, it's fine, but above, it's not. And on the line here would be the totality of dark matter. Now, this line here, this is microlensing constraints. And here, it's like evaporation. So you want your primordial black holes to not evaporate in the lifetime universe. And you also need to look into galactic emissions and some other astrophysical. I mean, there are several. This is the thing that I'm still studying, but there are several constraints that are encoded in this line, which have to do with the emission, photon emission from. Related to these primordial black holes. But of course, you want them to be stable, otherwise they could not be dark matter. This is the mass of the primordial black hole in solar masses. And what you see, there is here a window of a small window, where these primordial black holes can eventually explain the totality of dark matter. And what is interesting is that you have a connection, and this is because of the nature of this type of scenario, the classical scale invariance. So when you set the scale, when you set the scale with this the second Higgs boson scale, you set the scale of the neutrino, set the scale of this real Procca field, and you also indirectly going to set the scale of this primordial black holes. Everything is related here. And you see, so here in this region, you have if you are in this Z prime mass between 10 to the 6 and 10 to the 11, you can aim at explaining the dark matter. But okay, the same for neutrinos. So you can also find some regions. So y nu 10 to the minus 4, 10 to the minus 2. But what I want to say, the most important message here, and this is the last slide, is that this represents, now so it's the same plane, but this represents the signal to noise ratio at LIGO, this one at Einstein telescope, and this one at LISA. And LIGO, it's LIGO 05. And what you see here is that to have a signal to noise ratio above 10, which means that you can say something, you want to be like in this orange and the red region. So you can test basically this region here. So this means that with LIGO, with the 05 data, you'll be able to say something about, of course, all this region, but you can say you can start putting more constraints here in this corner here to see if there is viability for dark matter in this form or not. If you go to Einstein telescope, you have even more. It goes all the way down to here, to this region here. And in LISA, you see in LISA there is an inversion of the colors here. So LISA goes from its what was left goes to right. So you go more or less to cover all this region. There is some overlap with Einstein telescope even. So what do I want to say with this is that in principle, even before I retire, I will have a full picture about this. It's not like the FCC that maybe before I retire, there will be the machine will not be built or will be starting to to take data. But here it's something that is giving me the hope that, and if everything goes with current plans, so they are saying so. LISA is mid of next decade. Einstein telescope, I was reading in their webpage, they in 2 years are going to decide where the construction, they are talking about Germany or Italy. There are some discussions. I think Germany, it's more towards Germany at the moment. But it's going to be launched also in next decade sometime. And LIGO, it's there. It's, I think it's, I don't know if it's taking data now or not, but the release is like to 2028. Maybe you guys know more about that. But the point is, I don't need to wait, we don't need to wait until 2050 or something to have a full picture about what's going on here. And so this is my personal view on this, that it's a promising avenue that I really want to explore. Okay, so before coming here to the, okay, I will skip the conclusions now. But yesterday, Haroldo and Caio, they have shown Salinas and Maranhão. Haroldo is not here, right? No, Haroldo is not here. I also want to follow their example, and this is not where I work, but this is like this conference that, so I'm not the organizer, the main organizer is Rui Santos, but there is going to be this conference called My Favorite Dark Matter Model. Dario, take this in. And this is going to be in Azores Islands, which are really volcanic, really, it's a natural paradise, these islands. And everyone that wants to say something about dark matter in the most, Carlos is going to be there, for instance. Uli, boson stars are a candidate for that. You can be there. And this is going to be April. This is going to be Easter holidays. I should not have said holidays now. But this, guys, think about this. Of course, I understand commitments and other things, exams, all of that. Myself, I don't know it's going to be my funding situation next year. I really want to go, but I need to work out that before. But I really want to go, and you are all welcome. Okay, so thank you very much.
Thank you very much, Antonio. Is there any question? Okay. So I had one, and it's, so if you detect these models either with LISA or Einstein telescope, is there any kind of signal that characterizes this model, or it could be overlapped?
You cannot detect this model. You can interpret a signal in the scope of these models. But if you have a signal, you can rule out a lot of models.
But then you were saying instead of constructing a new particle detector, then that could be a...
Not even with the particle detector, you cannot detect a model. It's the same story. With the particle detector, what you can do, you can directly discover a particle. And say this particle fits in this model, that model. The Higgs boson fits in every single model. And only one can be right. So you see, this is just to say that with colliders, we don't detect models. And here it's the same. The difference is that here you cannot detect a particle, but you can interpret data in the scope of a given model or a family of models, and you can rule out another family of models. For example, if there is a signal, and it's a real signal, this requires a first order phase transition. And if the signal is associated to this first order phase transitions with a strong likelihood or something like that, then you need your particle physics model to explain that. And it's not easy to have a particle physics model that explain. So typically, in most of the scenarios that you have, right? Okay, it's sufficient here. So you have many points that fall behind here already with first order phase transitions. To get into LISA, even near this region, sometimes it's difficult. Now this is with classical scale symmetry is a different story. You have it's a different type of scenario that gives a lot of data. But that's the thing. If you see a signal, you can rule out a lot of stuff. And I think that's the most promising avenue. This is what I'm most hopeful for. To see something stochastic that can be of cosmological origin, and you can rule out most of the models in the market. Right.
Thank you very much for this amazing particle
Thank you.
physics.
I'm wondering about this deformation of the bubbles and taking into account that, well, you mentioned that you were also in the LISA consortium talks and you were paying
Yes.
last summer. Do you think that the consequence that we have with the theory of particle physics lead us to these bubbles without any assumptions, or there are some assumptions that they are probably hidden and we are not completely sure and we are taking into account then?
So that's a very important question. That's a really good question. So the point is that these bubbles, these are hydrodynamic simulations, and typically what is assumed is you have like you have a plasma with a it's a scalar plasma, scalar field. So and then you do the simulations based on that. It's kind of a Higgs Higgs plasma. Let me call it this way. So the point here is when you have a weakly coupled theory, in principle, it's okay to have that and extrapolate for the other models. If you have a strongly coupled theory with when you can have condensates, hadrons, this all sorts of things, maybe it's a little bit more shaky ground, at least from my point of view. You have a lot of nucleation points because it's a dense medium, so it's hard to. But when it's a weakly coupled theory, the current simulations they are reaching an increasingly good level of precision. Errors which are order unity, but not of order several orders of magnitude as 5 years back. But yeah, one of the things that is done is like you put one scalar field there and you do your simulations. What would be optimal? It would be to put all your model there. And maybe you could start seeing some features in the bubbles. I still think that can be an interesting thing to do in the future, but it's computationally really very complicated, also technically. But it's but that's the point. I actually asked that question, that same question in this LISA meeting. So what about simulation with a full BSM? People were saying, oh, okay, yeah, that would be good, but it's hard. And we are accepting that these simple simulations in a weakly coupled environment is fairly good already. But yeah, the point is the spectrum, this shape that is here. Okay, I drew this by hand, but the spectrum, the question, and that's a question that I have. And actually, this is something that I challenge these hydrodynamic people. So, what if you put your BSM theory? What if a way of simulating all our BSM stuff? Would we have some weird bumps here or there, or could it? Because then, what we can do now is parameter reconstruction. We can have data, or inject data, and we can reconstruct the parameters of theory. But parameter inference we cannot do because the shape is the same for all the models that we are using at the moment. So that was a pretty good nailing down question. Thank you.
Is there any other comment or question? So let's thank you again.
Thank you very much.